Okay, before we go any further in graphing quadratic functions, we need to get a couple bits, a couple things out of the way, a couple techniques, as well as some jargon that we use to describe quadratic functions when we're graphing them. So if you remember, if we have a function that looks like this, then this slope or the derivative of the function would be positive there. The derivative of the function would be negative there, okay? Because remember, the derivative is just the slope of the function. Well, if moving that direction in the x domain, we go from a positive derivative to a negative derivative, then that function must have a point where the derivative f prime of x equals 0, okay? And specifically, not only does f prime of x equal 0 at that maximum, but this particular dynamic in the slope, in other words, positive to 0 to negative, means that this function is also what we call concave down. And we would describe this concave down function mathematically by taking the second derivative and figuring out whether the second derivative is less than, equal to, or greater than 0. When a function is concave down, this second derivative should be less than 0, okay, at least in that range of x. If we have a quadratic function that looks like this, then we're going from, and we're moving to the right in our x domain, then we're going from a negative derivative to a positive derivative. And so again, somewhere in between, f prime of x must equal 0. Now we call this a minimum, a minimum, we call this a minimum because it is characterized by this negative to 0 to positive dynamic in the slopes. Mathematically, we would describe this as concave up, okay? And we would know this again by the second derivative. Now, if this was a function was concave down and the second derivative was negative, obviously this second derivative should be positive, okay? So we can figure out the concavity of this function in two ways. We can figure it out by just looking at the dynamics of the slope, okay? Here, positive, 0, negative. Here, negative, 0, positive, okay? Or we can tell the concavity of the function by taking the second derivative and seeing how it relates to 0. Makes sense? Let's do a couple. We're just going to do these mathematically. We're not going to worry right now about graphing them. But let's assume we have f of x equals x plus 2 squared. Okay, so if we take the first derivative of this function, we get 2 times x plus 2, or 2x plus 4. Okay, now that in and of itself, just looking at it, doesn't tell us much, but It actually tells us a lot if we look a little deeper into it. Why? Because this derivative can be positive or negative depending on the value of x. Okay, now the question is, okay, so this derivative, this slope of this function can change from positive to negative or negative to positive, okay? We don't necessarily know which yet. We could figure it out by plugging in x's, of course, but we're not going to do that yet. We're going to go straight to that second derivative because that definitively tells us whether we have a concave up or concave down function. And the second derivative, which is simply the derivative of the first derivative, is equal to 2, which is greater than 0. So this function is concave up. Now, so then what's the importance of that first derivative? Because if you remember, for this concave up function, it's got a minimum where f prime of x equals 0. So this is f prime of x. Let's set it equal to 0 and solve for x. So we get 2x plus 4 equals 0, or x equals negative 2. Haha. So what does this mean? That minimum is at x equals negative 2. Then how can we find the y-coordinate of that minimum? Simply plug that back into the original function and solve. Make sense? So now we've gone leaps and bounds in thinking about how we can actually graph these different functions by incorporating both the first and second derivatives and analyzing those derivatives in relation to 0. Let's do another one. Let's assume we have f of x equals 4x squared plus x minus 1. Okay? Now, the first derivative of that function, of course, is 8x plus 1. The second derivative is 8, which is greater than 0. Again, concave up just like this function. Now, if it's concave up, it's going to have a minimum. How do we find that minimum? We set the first derivative equal to 0. 8x plus 1 equals 0. That means x equals negative 1/8. And that is the x-coordinate of our minimum. To find the y-coordinate, we would simply plug 1/8 back into f of x. Let's do another one. I just used the bottom of the paper here. Let's do another one. Let's assume we have negative x squared plus x plus 2. F of x equals this. Okay, so what's the first derivative? F prime of x equals negative 2x plus 1. What is the second derivative? F double prime of x equals negative 2. So this function is concave down. It looks like this. Now when this function's concave down, it's going to have a maximum. How do we find that maximum? We know that's where the slope is 0, so we set the slope equal to 0. Negative 2x plus 1 equals 0. That means x equals 1/2. How do we find, so this is that maximum, that maximum is at x equals 1/2. How do we find the y-coordinate of that maximum? Well, we take that 1/2, plug it into our original function.